All right, so we are now going to talk about finding some more volumes. The last time we did this, what it was is that the volume was found because they gave us two pieces of info, which is like your base is this shape or this region, and then your cross sections look like this. So for this though, what we're going to do is that our cross sections are going to actually be kind of uniform for this. So these are what are sometimes referred to as solids of revolution or solids of rotation, because every single solid we create is going to be based around rotating something around a line. So like most of the stuff we end up getting will look like bowls and vases or vases, depending upon what way you like to talk. So like that's kind of the idea, is like we're going to create a bunch of like really pretty like dishes and vases and bowls and figure out what's the volume of them. All right, so let's start out with this problem here. It says we're going to find the volume of the solid obtained by rotating the region bounded by y equals x squared, x equals 2, and y equals 0 about the x-axis. Okay, so the first thing we are going to do is we are going to focus in on this part. I'm going to start two-dimensional with this. So the region bounded by y equals x squared, x equals 2, and y equals 0. So let's graph that. So let's see what that looks like. So I'll draw my coordinate plane real quick. So here we go. Y equals x squared. That's a parabola, like so. Boom. X equals 2. That's a vertical line out here. That's 2. So draw that, like so. And y equals 0. Well, that's just the x-axis, like so. So what's the region bounded by all of them? Take a moment to think about it. If you said it's this weird curvy triangle piece, you are correct. All right. So now that we know what the region is, we want to rotate it around the x-axis. So we're going to take this big sort of triangular curvy piece and we're going to rotate it around the x-axis like so. So here we go. We're going to try to represent a three-dimensional object in 2 dimensions. Let's see how this goes for us. So what I usually do first when I do these things is I reflect the shape over to the other side. So boom, boom, boom. And I try to draw it again. And then I try to show that it is three-dimensional by sort of adding in a little halo around the parts that are sort of circular. So this is our solid piece here. It's a Hershey's Kiss, or like I was going to say something that's like, but I don't think you guys would remember the reference. Anyways, so yeah, it's like a Hershey's Kiss. It's like the end of a trumpet. It's got that sort of thing going on with it. All right. So how are we going to find the volume of this now? Well, here's the deal. We're going to take a cross section of it. So we're going to cross section it perpendicular to the axis that we rotated it about. So since we rotated it about the x-axis, we're going to cut it like this. And so when I cut it though, and take a little chunk out, I'm going to get sort of like a little disc that can come out of it. So if I cut it here and here, and then pull it out, what I end up with is something that looks like this. So a nice solid piece there, just a disc, or you know, like a little mint, if you will. I don't know why I talk about food so much with these things. Anyways, so now we're going to do exactly what we did before, which is focus solely on this. This is basically just a little cylinder. It's a very tiny flat cylinder, like a coin or a mint, like I said. So let's focus on what the volume is. And the way we find the volume, is we just think about what's the area of the face of it, and then multiply it by the depth. Let's figure out that depth real quick. That depth is this little length right there. It's horizontal, it's tiny. What do we call it? Dx. All right. The face of this, though, is a circle. So how do I find the area of a circle? I got to find the radius here. So let's think about that. The radius, come back over here. The radius is determined by this curve right here. That's y equals x squared. And the radius is a vertical distance, which means I want to know what is the y coordinates, but in terms of x. So this will be x squared. All right, we've got all our dimensions labeled, so let's now talk about setting up our integral. So the integral, we start by thinking of just the volume of this. So I want the area of the face to start out with. That is going to be pi times the radius, which is x squared, squared, times the depth of my coin here, dx. Just as we did before, though, there's not just one little coin here. There's not one little disc. There are an infinite number of them. Where are they starting? Well, in terms of x, they're starting as far left as I can go right here at the vertex there, which is x equals 0. And then we build them, stack, 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 stack until we get to this vertical line, which is the line x equals 2. So to 2. Great. Quick simplify. Pi is a constant. We can yoink it out. X squared squared is x to the 4th. Pi coming out in front here. And there you have it. That's the setup. I'll leave it to you to finish it out by hand if you'd like. But also sometimes we get calculators, so maybe do it by hand and then calculate it on your calculator to make sure it makes sense. Okay. So, quick recap. Graph the region, rotate the region, pull out a disk, find the volume of that disk, and then think about an infinite number of disks. So let's take a look at a similar but slightly different problem here. So here we want to find the volume of the solid obtained by rotating the region bounded by, this time, same parabola, but then it's the horizontal line, y equals 4, and x equals 0, and we're going to rotate it about the y-axis. The y-axis. Okay, so let's do that. So again, focusing on the 2D first, so let's graph this region. So still got the parabola, like so. Y equals 4, that's maybe like up here. And then, I've lost my train of thought. Oh, y equals 0, that's it, right there, cool. So we're focused in on this area right here, which also happens to be this area. This is a nice one because if you remember, on the last one, the next idea was let's reflect that region. Well, it's already reflected over, so I'll just sort of go over it again here. And then I will just draw in the lines and shade in the region here. So there's a bowl. That's I was talking about, the bowl. There you got a nice little bowl for us. So we want to find the volume of that bowl. So this time, the cross sections, we're not going to cut them in the same way we did up here. So we cut them up and down because we rotated around the x-axis. We want to cut perpendicular to that axis of rotation. This time, our axis of rotation was the y-axis, so we're going to cut it this way. So let's do that. So if I cut across like so, then I get this little disc here. Let me pull that out. I always like pulling it out of the figure so I can draw it a little bit bigger and focus in on the important things. Okay, so this time the the depth of my disk is a tiny vertical length, so we'll call that dy. And then the radius in this particular case, all right, well this one I think we're going to need to do some stuff here because I want everything in terms of y. That radius is dependent upon the parabola, but the equation is in terms of x. So let's do some quick solving to make sure that we get the correct stuff going on here. So we're going to take y equals x squared. If we take the square root of both sides, we get positive or negative square root of y. That's equal to x. Well, which one is this? Which arm is this? As it turns out for this problem, it's not going to matter, but sometimes it totally does matter. So let's be sure we know why we're going to choose the positive or the negative. So if we're finding x values here, are the x values over here positive or negative? Well, they're positive. So which version of this should I use? The positive version. So this arm over here is x equals positive square root of y, while this arm over here is x equals the negative square root of y. I didn't draw my negative very well there. There we go. Okay, so with that in mind, coming back to the disk, the radius can be found by taking the square root of y, the positive square root of y, or the principal square root of y is what it's called sometimes. Okay. Oh, I forgot to shade this in. I'll shade it in. So this is all solid. Our next step is going to be when we have sort of gaps in our solids, but we're going to be starting with everything being just a big solid piece right now. Great, so now let's talk about setting this up. So how do I find the volume of this disk? Well, same way I found the volume of the disk before. The face of it is a circle, so pi times the radius squared, and then multiply it by the depth of it. So then what do we get? Well, we don't want one disk, we want an infinite number of them, so we're going to go the integral from, and then come back over here. What's happening? So if we think about this picture here, the disks now are not being stacked left to right, but instead on top of each other. So there's a tiny disk down here at y equals 0. We care about y because everything is in terms of y. And then we stack, 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 stack until we get up to this horizontal line is where it cut off, which is at y equals 4. Once again, we can yoink out that pi, and then if we square the square root of y, since we're only dealing with positives here, we know everything is going to be just fine. That's just y. And there you go. You will come up with the appropriate answer here. Again, maybe do it by hand first, and then check it on your calculator, okay? So that'll be an easy way to check, because I don't know the answers off the top of my head, but your calculator will tell you what the answer is, as long as you plug it in good. All right, so please take the survey after this and answer there's a little multiple choice question just to see if you get how to set this up. And then come in Monday ready to work on things just like this. All right?